Okay, the first lesson in this energy unit is going to be about, three different concepts that actually run very, very closely together. States of matter, phase changes, and phase diagrams. Now, this really just plays on some of the topics you've been hearing about your whole life, so this is more of a review type lesson rather than a lot of new information coming your way. So your three basic states of matter that naturally occur very commonly on Earth are solid, liquid, and gas. Now, as we talk about a solid, a few things are important to keep in mind. First of all, solids are very tightly packed, and another way to think about them is they're also very organized. They tend to have a rigid structure, which keeps them in an organized and repeatable pattern. They have a very strong intermolecular pattern in attraction to one another, and for the most part, we're going to say that they're going to have very high, call it near 100% intermolecular attraction between the molecules that make them up. Now those molecules, because they're so connected to each other, next to each other, from one to the next, to the next, to the next, to the next, and so forth, they form this rigid pattern. Because of that, they're very restricted in how much they're able to move. They're also restricted in the amount of space that they have to move because they're very tightly compacted. Now, because solids are rigid and they have all these connections between one another, they're not compressible. If you were to hit most solids, and we'll explain the exception in a moment, you would actually cause a shattering to take place. Now, think back to earlier in the year when we actually did hit some solids and they didn't shatter, they actually flattened. Well, that was a little bit different. That when we were hitting metals, they did not actually shatter. Those metals actually shifted and caused a flattening effect called malleability. That was due to the flow of electrons, the movement of the electrons not causing that rigid of a structure. So in essence, they were not as connected to one another. Liquids are not held as closely together. Now there are certain connections made at the intermolecular level in liquids. However, it is going to be less than 100%. Now, because there's different thicknesses of liquids, we have to introduce another word, and that word is viscosity. Viscosity refers to kind of like the resistance to flow of a particular liquid. So a high viscosity is going to be much closer to a solid up here. So this is high viscosity, and low viscosity would be closer down here, closer to a gas level, which is going to be 0 intermolecular forces. So a liquid is somewhere between that 0 and that 100% in terms of the intermolecular forces. Now liquids will take the shape of their container, however, they will also have a free surface, and that free surface is the top surface that is unshaped by the container. They have some movement, more movement than solids, but not as much as a gas. And this really should be incompressible in terms of liquids. When you try and compress a liquid, they simply move out of the way. Now gases, on the other hand, we're going to talk about in a little bit greater depth with the next lesson. Gases are very far apart. The molecules are very, very far apart from one another, not close enough to form any type of weak attraction called intermolecular attraction. Therefore, they have a 0 on that scale, and they're allowed free movement. Because there's a great amount of space in between them, they are easily compressible. The fourth common on Earth state of matter is plasma. Now I say common on Earth because you actually find it somewhat. But when you look around the universe, 99% of all matter in the universe is plasma. That's because outside of our solar system, most of the material that's out there is actually in the form of stars, and stars are made up almost exclusively of plasma. Now the key note about a plasma is it's extremely hot. And hot is really just extra energy. So there's so much energy moving around that the nucleus can no longer contain the electrons that are flying around it. Instead, those electrons shoot off. And so what you get are charged electrons and charged proton nuclei areas in this plasma. Therefore, one of the primary differences between a gas and a plasma is the fact that a plasma is a good conductor of electricity, whereas a gas is not. They contain negative and positive charges, but they're very similar to gases in other regards. For example, they have an indefinite shape and an indefinite volume because of the vast space in between. They're also easily compressible. One of the things we can look at with our different phases of matter is how we change from one to the next. And there's two ways of really looking at it. We can be endothermic or we can be exothermic. Now an endothermic phase change is one that heat must go into. So energy goes in. Energy goes in. And I colored this in blue because it actually has a cool feel to it. The reason it feels cool is because energy is being pulled from the environment, and we're part of the environment. Exothermic, on the other hand, means energy is exiting. Energy is leaving. And as energy is leaving the system, we are part of the surroundings on the outside, and we actually feel that. So this feels quite warm, sometimes hot. So we're going to go through these processes here. We're going to give them a color, endo or exo, blue or red, in order to get an understanding about what we need to do. So think carefully. When you're going from a solid to a liquid, does that require energy, or is that something that gives off energy? Okay, well, to go from a solid to a liquid, you must add energy to that. So because we're adding energy to that, this is going to be an endothermic process. The opposite, freezing, is an exothermic process. We are giving back the energy, and the energy is leaving. Okay, so we can go through, we can label all of these, and the processes involved. So think about going from a liquid to a gas. Energy must go in. That's called vaporization. Condensation is the opposite process. We can go ahead and label all of these in that process. Anytime you jump to a higher state of matter, a higher temperature, you're going to cause an increase in energy. Increase in energy means energy has to go in, and therefore it's going to be endothermic. Finally, all of these can be represented on what's called a phase diagram. Phase diagrams are specific to one particular substance. And a phase diagram is great because it shows multiple sources or multiple states of matter all at one time. So if we look at this top left one over here, you notice we have temperature and we have pressure. Well, a phase diagram shows the different conditions under which something will work. So this first one up here in the upper left, this is water. Okay, and I know it's water because the temperature of 0 and an atmospheric pressure of 1, we are talking about the melting point, the point at which we are transitioning from a solid into a liquid. Now as we increase our pressure, as we move up, what do we notice about the temperature required to cause that melting to occur? Hopefully you notice the temperature required actually decreases. So some things to note on a phase diagram is that we have multiple phases, solid, liquid, and gas. We also have a very special region where all three of these things simultaneously exist, and that's called a triple point. A triple point is the point in which all three phases of matter will simultaneously exist under the right pressure and temperature conditions. Also, all 6 phase changes are likely to occur at this particular point. The other interesting point to look at is called the critical point. And the critical point is the point at which the temperature and pressure actually force a substance into a state where it can no longer be a liquid. It either becomes too compressed and it is a solid, or it is too hot to be a solid and it's in its liquid state. For our test, you need to be prepared to understand the differences between the states of matter and how you could use a phase diagram to predict a different state.